Hello class, today we're going to work on vector and parametric equations, but we're going to start with one question as a warm-up. So for this one we're going to try and find point P that is 4/5 of the way from point A 7, -2 to B 2, 8. Take a moment and try this one out. We're about to review it. So for this question, if you began writing out your equation, that's perfectly fine, but I'm actually going to start off with a drawing and say that we have point A being, let's just do a quick notch diagram here, that A is 7, 2, so 1, 2, 3, probably make that better, 1, 2, 3, 4, 5, 6, 7, and we have here, we actually probably should go up to 8 for our vertical axis for the other one, and for this case 7, -2, probably should just at this point just do some more. Okay, that should be enough. A is going to be 7, -2, so that's going to be approximately here. So this is point A, 7, -2, and we have 2, 8 for point B, and this is going to be 2, 8. Try to do a straight line there, and this is now our AB vector. Alright, so if you recall from the last lesson that this idea was if we have our origin here, right, and we're looking for some point P, we'll put point P as blue, along this path. 4/5 you might say is over here in this area. We'll double check that later. But if you were saying it was in that area, how do you prove it? Well, the best way to prove it is this idea of considering the idea that you're running a marathon. Being that here, this is your beginning point, your home base, where you sleep, your dorm, wherever you'd like, and that here is the start of the race. This is your starting position, so I'll write starting or initial position. Starting position, and you're about to run. Let's see if can I draw a runner on here? My art skills are really coming in handy now. Alright, runner's about to go. You have to get from the origin to this starting position. So we call this vector OA. Well, to find our other vector for P, I forgot to label P here, to find our P point, we can actually say that this is going to be the OP vector. OP. And this is some X, Y position. Now, I bring this all up because what's the interesting bit about this is we can actually assume for the runner is going to run at constant velocity along this path. So let's say you're their friend and you're trying to catch up with them at a certain point, and you're saying, hey, when you're 4/5 of the way there, right, or you're, sorry, not, we shouldn't say that in terms of distance, let's say you're expecting them to complete it a certain amount of time, and you want to meet them at a certain point, right, and you're saying where that 4/5 of the way there of their time estimate is going to be, that is going to be some position here. Let's say if you picked a place in town, you said the route was starting off, I don't know, in New Haven, and you're ending up somewhere in North Haven, or I should say here, North Haven. And this is somewhere along the way, let's say a McDonald's, that you wanted to see them at. I'm picking some generic places just for sake of examples. But basically this 4/5 acts as a time, because I'm going to draw this here, because our equation actually is very simply this idea that we have some X and Y position we're finding for our P position. So this is P. Okay, this is point P, is going to be equal to the X naught and Y naught plus some time multiplied by the AB. Now, what's interesting here is that time, this is going to be your fraction. Let me underline this. And the AB is going to be the vector for these two. But the thing is, these are your velocity vectors. You're assuming a constant speed for the duration of the race, as in you didn't slow down, you didn't speed up during any point. Granted, that's not ideal. And this here is going to be your starting position. Starting position, which is going to just simply be A here. And that's your vector equation. So this is taking a little bit from the last one, the last lesson, and applying it here. Now, why I say all this? Because it's practically the same equation, and we're applying it in a new setting. So with everything being set up, let's actually plug things in. So in this case, we have x naught, y naught, and that's going to be our 7, -2, that's your starting position, plus the time, which is 4/5, and this is the part where we actually have to calculate the vector for the AB vector. So let me do that in purple. I'll do this down here. AB vector is simply going to be x2 minus x1, oh, no parentheses, comma, y2 minus y1. You always do final minus initial. And in this case, you're going to get your final, which is 2 minus 7, comma, 8 minus 2. You're going to get -5 and 10. So this is going to be -5, 10 here. Just for symmetry, I like to have blue here. There we go. Okay, so let's keep going through. I think I had a different color the other day. I'm trying to remember which one it was. Don't think it was that one. All right. Yeah, I like that one. Okay, so if we keep going through, 7 to, you would end up, as the steps we mentioned earlier, we're going to start off with find this vector. Find that vector. Multiply by the time. Then you're going to add your initial position, your x naught, y naught. Okay, so let's do that all together. So we're going to multiply this out. You're going to get, this one's going to be just -4, and this one's going to become 8. Okay, you can feel free to do that one out. And we're going to add our like terms here. You're going to get 3, and this is going to become 6. And there you have it. That is the position you'll be found at position P if you're trying to look for your friend. So this should be 3, 6. Did I actually come close? What was it? 1, 2, 3, 4, 5. Ooh, should have been like here if my graph was vector was drawn correctly. Close-ish. But if I were to rewrite this, this would be 3, 6. And that is my new position vector. Position for where I'd find someone at 4/5 the way along the AB vector. So overall, that is actually our first part of this lesson, the vector. And that's reviewing from the last part of the lesson as well. We're going to hit now parametric equations. Alright, so let's actually refer to our last vector equation we just used, which is here. This one. Now, for this one specifically, we were using it for a specific point we were looking for, based on this time given. Now I want to rewrite this for any x and y position. Well, that's all based on this here, time. So if we want to make it for any x and y, we have to actually get rid of this and make this a variable. And I already said it before, well, that's going to be your time variable. So this is for vector equations. And this is our vector equation for here. But if we actually look at our motion for this, let's use blue for x motion, and we're going to use red for y motion. If you have these two, right, they're two independent motions along one axis and along the other axis, but both based on time. So if I were to pick any time, let's say t1, well, I'd be at some position x and some position y. Together, if I had to say, if I'm using both of those motions, I end up somewhere here at that time that I was just looking at. But basically, together they come up with a resultant. Let me redo my arrow here. they come up with a resultant that looks like so. Because that is the addition of this vector plus this vector. But the total motion together creates this motion here of going in this direction. Not just to the right, not just up, it goes diagonal. So, that is actually represented with these two components. So how do we write component equations? This is what we refer to as our parametric equations. They are the individual equations for our components, aka the component vectors. So let's write one out. I'm going to do the x first. Well, if I'm looking at the x motion, this is x equaling something, we have, for this given problem, we have the initial point x plus t with this x velocity here. Now, the key point to note is that -2 and 10 don't affect the x motion. So actually, we have 7 minus 5t. That's it for this. We only look at our x's, which are following here and here. And what affects the x? Well, time. Time will affect also the y, but the y's don't affect the x, and the x don't affect the y's. So when I do the y motion now, y is simply going to be -2, that's your initial, plus 10 times t. And that's it. That's actually really simply what you're going to get for your parametric equations of x and y position. Now at this point you must be asking, how is this helpful? How does this work at all in a question? And at this point the video is getting a little bit long, so I'm actually going to stop it here. There will be supplemental work and worksheets for you to work on if you'd like to apply this, but the best way I can tell you is here time is a parameter that's constant between both dimensions x and y. So in a lot of cases you'll be solving for time and replugging them into one or the other to find the x or the y position based on time. So we'll go through some practice problems on your worksheets with some solutions. Feel free to try those out and let me know what you think. Alright, thank you for joining me and look forward to seeing you all next time.